Hi everyone, especially to Dr. Evan. My name is Lam Xue Li with message number 7555. Without further ado, let's go to the question. The question is about COVID-19. We are asked to do a estimation for the model, as you can see. And the case I choose is Japan. Now, question 1. Question 1 is about unit root test. Unit root test is very important for the researcher to test the stationary of the data. So now let's go to the result. There are totally three types of unit root test, which is the first one is ADF, the second one is PP, and the third one is KPSS. And then before we discuss about the result, let me discuss about the hypothesis first. So the null hypothesis and the alternative hypothesis. The ADF and PP, both of it actually share the same hypothesis. So null hypothesis would be there is a unit root. And the alternative one is no unit root. I just write UR. And for information, no unit root is equal to stationary. Okay. So, but KPSS is different. The hypothesis of KPSS is terbalik. I say terbalik one. Okay. So the asterisk here is means significant at 5% level of significance. And if it is significant, then we reject the null hypothesis. As you can see, all of these for ADF and PP, for both trend and intercept, both are rejected. But here always remember that the KPSS hypothesis is different, but there's one asterisk here, means that this is not stationary, but it's just okay because we use 3 and 2 of the method actually suggest the same conclusion. So we can conclude that conclusion. All variables are stationary at level. Certainly, we don't need to go to first difference, as all of the variables are stationary at level. So we don't need to go to first difference. So it is the conclusion of this unit root test. It's very important. If it is not stationary, we have to modify our data or figure out some other methods. But in this case of Japan data set, the result is what favorable. So now we move on to question 2. Question 2 is about co-integration test. Co-integration test is very important for us to determine the long-term relationship, whether the variables have co-integrating vector or not. So in this case, I use Johansen-Juselius co-integration test. So the same meaning of this asterisk means significant at 5%, and or we can refer to maximum eigenvalue and trace. Both statistic actually suggest there is reject. We look at this. We compare the value of this to the critical value. So it's actually reject. So we conclude with alternative hypothesis that R is actually equal to 3. But how? What is the meaning of R equal to 3? Is how much depends on how many variables we have. In this case, we have 3 variables, and the R co-integrating vector is actually 3. So we can say that it is full rank. Why is full rank? Because the R is same, the number of R is same with the total number of variable, including dependent variable, all the variable. The number is the same. So we conclude that it is full rank. Full rank means that 3 co-integrating vector with 3 equilibrium. I just write the simple form, and then limitation of this is that it is difficult to actually detect the co-integration among the stationary and near integrate variables. It is limited, so we certainly cannot go with VECM. So now we will go to WA. This is the result. Let me wait. Okay, let me draw a text box because I want to jot down my notes. Okay, here is the Granger Causality result based on WA. Remember this, based on WA. So it's the same meaning that the asterisk means significant at 5%. So here we can see there are two. There are actually two. Two. Where? From ND, NC, and then NC and D. Okay, for better understanding, so we normally will adopt we draw out a figure, a diagram for us to understand easily. And here, as you can see, the error is two-way. New depth Granger cause new cases, and also new cases Granger cause new depth. Is in the short term, the relationship that they actually cause each other in the short terms of time period. So we can say that I just write down new depth and D. I just write ND cos NC and NC cos ND. So there is a bidirectional relationship, and it's two. We have two direct relationship. Yeah, from ND to NC and NC to ND. Okay, now I move on to question 4. Question 4 is about variance decomposition. It is actually for question 4 and question 5 is estimate the sample. We want to forecast the result beyond the sample size, beyond the sample. So for your information, as this is daily data for COVID-19 daily data, right? So we use 180 180 horizon in forecasting. We want to forecast how is the impact, how is the influence for this horizon. So now normally I will just combine the result from the table and also the graph. But before I just look at the graph first, the graph for this variance decomposition. Okay, now we can see this is the variance decomposition of new depth, and the blue color one is new depth, and the green color one is new cases. As you can see, at the beginning, the variable explained itself at the beginning 100%, but it drops significantly and remain is around 75. Starting from 75 horizon, it remains a certain level, but we can see that the impact towards itself is actually decreased decrease in this 180 horizon. We can say that it dropped, and it is explained by the other variable named new cases. So new cases give a big impact on new depth. So now we look at new cases. New cases is green color, and the depth is blue color. We can see it dropped, the impact drop, but most of the time the new cases explain itself. Okay, now we look at the stringency index. The stringency index is in orange color, and the red one is the green one is new cases. The impact of new cases towards stringency index is actually increased. We can see, but the main impact is the variable itself towards itself. But we can actually conclude that the most exogenous variable is STI, stringency index, while the most endogenous is new depth. I discussed just now, the portion, the impact towards itself, and see which variable is actually influence others and the other way around. Okay, now we can go to question 5. Impulse response function. It's the same. I choose 180 horizon, and let's see how is the impact of this variable, this short itself, and then how is the impact, when is the impact dies off. So now let's look at the response of new depth to stringency index. We can see at the beginning it fluctuated, and then increase and then decrease until it's around 75 horizon and become stable. And the new depth to new cases, it increased significantly. It dropped starting from around 28 like that, 28, yeah, starting from that, decrease and achieve stabilization, at around 150 horizon. And now we look at the stringency towards new depth. Is actually increased at the beginning, but decrease at around 10 horizon, and increase and fluctuated, and there is no stable, cannot achieve is stable. And then now is about I want to discuss about the new cases. The new cases towards new depth. It is fluctuated at the beginning, but not that long, but it's dropped and achieve stabilization. Is stable very fast. I mean it's stable very fast, like 26 or 28 horizon. It becomes stable, and then it drop again. The negative impact, it becomes negative impact. Is different negative impact, but the negative impact drop. So we can say that new depth is actually giving a positive impact towards stringency index and new cases at the beginning, but drop significantly and achieve stable later. So so hopefully this video make giving some information to you, and we hope that all of us can stay away from COVID-19. I mean not stay away, but just stay safe. And that is all my presentation, and thank you very much for watching this video and listening to me, and I wish you guys have a nice day. Bye bye.